I'm now going to make a short video introducing intermolecular forces for introductory chemistry students. So what does intermolecular force mean? Well, the prefix inter means between. So we know that inter means between. Molecular means molecule, and force essentially in this context means an interaction, an exchange of information. So when two molecules come together, they can interact either favorably and they can attract each other, or they can interact unfavorably and repel each other. In the former case, if they interact favorably, that would lead to an exchange of information that would result in either a liquid or a solid because of the strong forces of attraction between the adjacent molecules. If the molecules led to a disfavorable and unfavorable repulsive force, that would lead to the insistence of a gas present under otherwise typical conditions. There are four major types of intermolecular force that we need to be concerned with. And I'm going to abbreviate intermolecular force as IMF so as to not consistently have to write intermolecular force. So I'm going to write IMF, four types of intermolecular force. And I'm going to put them from the strongest force to the weakest force, and this is a good idea. So from strongest down to weakest. We'll have them like this. So the strongest type of intermolecular force is ion-dipole. And in a few minutes I'll create a new screen and we'll go into some detail about what an ion-dipole force is. Next we have hydrogen bond. Again, all we're doing for now is just listing what these forces are. Then we have dipole-dipole forces. And then finally we have London dispersion forces. So these are all forces. So maybe get rid of the word force here. So they go from strongest to weakest. Essentially, the more forces that you have present between two molecules, the more likely that that molecule will present under, let's say, room temperature conditions as a solid. The fewer of these forces that you have, the more likely the molecule will present as a gas under room temperature conditions. So I'm going to pause the video and change the board, and then we'll look at examples of these types of forces. Okay, so we're going to look at the strongest of the intermolecular forces first, and that will be ion-dipole. So an ion can either be a cation or an anion, and we know that a cation is just a positively charged ion, whereas an anion is a negatively charged ion. So that's an ion, and that's going to interact with a dipole. Now we haven't looked at dipoles yet, but for now a dipole, well, the prefix di means two, pole means end, so a dipole is just a molecule that has different ends. I'm going to abbreviate a dipole for now as just a line, a vector. So the length of the line is the magnitude of the vector. vectors have a direction. So this vector is pointing up. And I'm going to make a plus sign at the tail. And at the tail, where the plus sign is, that reminds me to put delta plus. So this is a Greek letter D, or delta. Plus for the plus tail of the arrow. And then at the head of the arrow, I'm going to put delta negative. So this is an abbreviation of a dipole. It's a molecule that represents a molecule with two different ends, a delta plus and a delta minus. The delta minus is a partial negative accumulation of density, electron density. So essentially, whatever atom is represented at the head of this arrow is pulling electron density towards itself more than, and conversely, whatever atom is at the tail of the arrow is pulling electron density to itself less favorably. So there's a mismatch, there's more electrons being pulled this way. So to use an analogy in a tug of war, the delta negative is winning. So that's a good way to think of it. Okay, so if we have an interaction between an ion and a dipole, then the cation could interact with the negative end. So there could be an interaction here. So cations prefer to interact with the delta negative head of the dipole, just because of opposite charges. So a plus and a minus, opposite charges interact with each other. And the negative ion, the anion, would prefer to interact with the positive end of the dipole. So this would be an attractive force, let's say force attractive, because they're opposites. You could also have repulsive forces. So if I were to erase these attractive forces, so I'll erase it real quick. Then I could have, so here I'm looking at the anion with the negative end and the cation with the positive end. These would be repulsive forces. So like charges repel, positive and positive repels, negative and negative repels, and opposite charges attract, as we saw previously. So an example of this would be, let's say, for example, a sodium cation and a chloride anion. So if you dissolve some sodium chloride in water, you'd have dissociation of these ions. And a water molecule would interact favorably with the oxygen end, with the sodium, and a water molecule would interact differently with the anion, with the hydrogen end. So just as we've got two ends of this dipole, we have two ends of our water molecule. So if I look at water molecule, and if I were to chop this in half, like that, and look just at the hydrogen end or the oxygen end and vice versa, well then here, if I superimpose the dipole, then the oxygen end would be delta negative, the hydrogen end would be delta positive, and as you can see, I'd have an interaction with the delta negative oxygen end. Conversely, I've switched the orientation of my water molecule here. So I would change the direction of my dipole. So my dipole now heads in that direction, still with the same labels, but now the hydrogen end with its delta negative is interacting with the anion. So I'll pause the video, I'll change the board, and we'll look at the next strongest IMF, which are hydrogen bonds. So now we move on to the next strongest type of intermolecular force, hydrogen bonds. There are essentially three types of element that can interact via hydrogen bonds. You would need, obviously, a hydrogen. Now the hydrogen must be bonded to an element, immediately bonded to an element X, where X must be either fluorine or oxygen or nitrogen. Immediately. There can be other things, but the hydrogen, remember, hydrogen can only form one bond. It must be bonded directly to X, where X is either fluorine, oxygen, or nitrogen. Likewise, there has to be another molecule I'm going to call it XR. Now X, likewise, must be F, fluorine, O, oxygen, or N, nitrogen. Here, R can just be, I mean it to mean any other element. So I'm really not interested in R. It's just anything else that we're not really focused on right now. And the hydrogen bond itself is between the hydrogen that I've drawn on the left and the X on the right. So this is the H bond. So not any hydrogen can hydrogen bond. It has to be a hydrogen that's been activated by one of these elements with one of those elements on an adjacent molecule. So it's a very exclusive club. An example would be the interaction of two water molecules. So two water molecules drawn here, a black water molecule and a red water molecule. I know that oxygen is one of these applicable X atoms, and hydrogen is an activated hydrogen because it's on one of these X atoms here. So this is an eligible hydrogen. You're an eligible partner to hydrogen bond. So we form a hydrogen bond here. I'll pause the video and we'll next turn to dipole-dipole forces. So now we'll look at the third strongest type of intermolecular force, the dipole-dipole force. Recall that a dipole can be represented as a vector, a line with a magnitude, a plus end and a minus end, so let's annotate that accordingly. We can write an adjacent vector again. So we've got an unequal distribution of electron density along here. And we know that opposite charges attract. So there's an interaction between the delta negative head of this vector and the delta positive tail of this vector. So this would be a dipole force. An example of this could be two water molecules. We can represent, remember, if we were to consider both sides of this molecule, the hydrogen side or the oxygen side, then we could represent that as the dipole indicated above. So the delta positive hydrogen end versus the delta negative oxygen end. Likewise, the delta positive hydrogen end, the delta negative oxygen end. And so the oxygen end would interact with the hydrogen end. So we could just represent dipole-dipole interaction that way. Very similar to hydrogen bonding. In fact, hydrogen bonding can be considered an exclusive membership of the dipole-dipole family. So I'll pause the video and we'll look at the fourth and final type of intermolecular force that we need to consider, and that's London dispersion forces. Okay, London dispersion forces are the most common type of intermolecular force because every atom and every molecule conceivable has them, because the eligibility requirements to have London dispersion forces are electrons. So London dispersion forces are proportional to the number of electrons. So every atom has an electron. Every atom, therefore, has London dispersion forces. Incidentally, London is the name of a German professor, not the capital of Great Britain. So that's an anecdotal fact. And they're also called temporary induced dipole forces. So induce means you have to do something to make them manifest. You can undo the manifestation, so they're only temporary. And when they do manifest, they behave like dipole forces. So for example, we can take a hydrogen molecule. So I'm going to draw the Lewis structure of a hydrogen molecule to illustrate the London dispersion force. So we've got the Lewis structure, we've got the two valence electrons between two hydrogen atoms. And I could have an adjacent molecule, again, with the two hydrogen valence electrons. I've got the hydrogen electrons equidistant in this illustration to represent the fact that hydrogen, there's no difference in electronegativity values between these two hydrogens. Okay, so as it stands, there is no interaction between these two molecules due to the large separation. However, as the separation gets less and less and less, so as the separation decreases, so if we draw them closer together, so I guess if you like, this molecule is moving that way, and this molecule is moving that way. So you increase the pressure, you compress the molecules together. The electrons, remember the electrons have a negative charge? Well, then we get repulsion between the electrons. And the electrons want to move apart, although the molecules themselves are getting closer and closer together because they're being pressurized by the externally applied gas, or whatever mechanical means of compression is being used. The electrons inside the molecule want to separate away. Okay, so this now has a difference, right? Here the electrons were exactly in the middle, and so both ends were identical. But now the electrons are not in the middle anymore. I've temporarily induced a dipole. This hydrogen has the lion's share of the electrons, and this hydrogen has the pauper share. Likewise, I've induced, because of this externally applied pressure, compression force, I've now got a temporarily induced dipole here. Well, there's still a repulsion, because whether you consider the electrons are repelling or the positive end of these dipoles are repelling, there's still a repulsion. But this is only one dimension I've represented here. Let's consider that this is happening in 3 dimensions, which it would be. So to represent a 3-dimensional fact, I'm going to, in good style, use only 2 dimensions. So imagine this is happening all over. So imagine this is happening down here as well. I'll just tilt the camera so you can see. So let's say I have my temporary induced dipole here and down here. So again, I've got my repulsion here, my repulsion here. Let's box these off, make it look similar to that. Okay, so repulsion here, but then you're going to collide into these guys. So we've got a delta plus here, a delta negative here, and there's my London dispersion force. London dispersion forces, again, are proportional to number of electrons. The more electrons you have, the stronger they get. Although they're weak individually, if you've got hundreds of electrons or thousands of electrons, for example, in proteins, these can be quite sizable. What else about London dispersion forces? London dispersion forces allow us to understand how you can liquefy a gas. So liquid hydrogen, liquid nitrogen, you can make something that's naturally a gas or a liquid, naturally a gas under regular room temperature conditions. By changing the pressure, you can induce, you can augment London dispersion forces, and you can lead to a phase change from the gaseous phase to the liquid phase. And this will conclude the short video on intermolecular forces.